Welcome. Today we're going to talk about section 8.7, power series. Power series is an infinite polynomial. A power series centered at x is equal to c has the form of the series ak times x minus c raised to the k, from k is 0 to infinity. So if you expand that out, it looks just like a polynomial. a0 plus a1 x minus c plus a2 x minus c squared plus a3 x minus c cubed, and on and on and on. An infinite polynomial. The numbers a0, a1, and a2, and all of those in front of the x minus c's are the coefficients of this polynomial. A lot of times we will center the polynomial at 0, so then the polynomial would have the form of the sum from k is equal to 0 to infinity, ak times x to the k, which is just a0 plus a1 times x plus a2 times x squared plus a3 times x cubed, and so on. These power series will have one of the three properties. They'll either converge over the entire number line, or they'll only converge at a single point, perhaps only at x is equal to 0. So let me specify or at a single point, depending on where the power series is centered. Or for some set of x's in an interval. The interval could be an open interval or a closed interval, or one end is open and one end is closed. The radius of convergence is the distance from the center of that interval to the end of the interval. So if you know the length of the interval, cut it in half, and you've got the radius of convergence. Given a power series, we're going to determine its interval of convergence using the generalized ratio test. So let me remind you what that says. The generalized ratio test says that we take the limit as k goes to infinity of the ratio of the subsequent term divided by the current term, or these are different a's than what I used as the coefficients above. These are the a's in our series, like that. So it'll involve the x's as well. So the generalized ratio test, look at the ratio of the subsequent term over the current term and look at that limit. If that limit is smaller than 1, then the series converges. That's what we're going to use. The other two parts were if that limit is bigger than 1, the series diverges. And if that limit is equal to 1, the test is inconclusive. So what we are going to do is take our power series and we're going to set up this limit, but we're going to choose L to be less than or equal to 1. So we're going to change the equal sign to a less than symbol, not a or equal to a strictly less than symbol, and use 1 for L, because we want to know where it converges. We don't give a hoot about where it doesn't converge. So here's an example. Here's several examples. Determine the interval of convergence for each of the following. So in our first one, we just have a very simple power series, 1 over k times x to the k. So started this one at k is equal to 1 so that I don't divide by 0. So it looks like 1 times x plus a half times x squared plus a third times x cubed plus a fourth times x to the fourth, and on and on and on and on. So we start with the ratio test. Set the limit as k goes to infinity. Take the expression, replace each k by k plus 1, then divide by the current expression, set it smaller than 1, and solve for x. So here we'll have the limit as k goes to infinity. So I said I was going to replace each k with k plus 1. Let me make a single fraction out of this. And then we're going to divide that by x to the k divided by k. So ak plus 1 divided by ak in absolute value smaller than 1. let's take it over here. We're going to do the flip and multiply step. And I'm also going to write x to the k plus 1 as x to the k times x to the 1. Then I flip, put this k here and the x to the k there. Keep the absolute value bars smaller than 1. Then the x to the k's can cancel. This x does not have anything to do with k, so I'm going to factor it out in absolute value and then take the limit with what's left. So we're going to have the absolute value of x times the limit as k goes to infinity. What's left is k over k plus 1. And I'm going to find the values of x that make that smaller than 1. You can see that that limit is going to be 1 because the degree on top and the degree on the bottom are first degree, so that limit is just the ratio of the coefficients. So this limit is 1. That leaves us with the inequality to solve that absolute value of x is smaller than 1. That 1 over there is called the radius of convergence. But that also means that x lies between -1 and 1. To see if my interval is closed at either endpoint, I go back to the original series and substitute 1 and -1 in for k. So we're going to check the endpoints of this interval. Let's let x equal -1. And our series looks like -1 to the k times 1 over k. If you remember this is the alternating harmonic series, and we showed that it converged by the alternating series test. The alternating series test had two parts. We have to show that the non-alternating part goes to 0, and we have to show that the non-alternating part is decreasing. So just an observation that 1 over k plus 1 is a smaller fraction than 1 over k, so that means it is a decreasing sequence. So by the alternating series test, it converges at x is equal to -1. If we let x equal to +1, then we don't have that alternating part. We just have 1 over k. And that's a divergent p-series. That's the harmonic series. So our interval of convergence is going to be closed on -1, but open on +1. So there is our interval of convergence. Next one. We've got 1 over k factorial times x to the k. So we start by saying the limit as k goes to infinity of ak plus 1 over ak is smaller than 1. So for this example, that looks like this. X to the k plus 1 divided by k plus 1 factorial. I'm going to jump ahead and do the flip and multiply step. That would put an x to the k here and a k factorial here. Again, x to the k plus 1 is the same as x to the k times x to the 1. So I can write my x to the k plus 1 like that. Also remember that k plus 1 factorial is the product of k plus 1 with k factorial. So when I rewrite things, oops, I don't want an x there, I want a k there. I want my k factorial here, x to the k there. Now let's do our canceling. The x to the k should always cancel. Here I got a k factorial canceling. The x to the 1 is not dependent on k. So we're going to factor that out in absolute value and look at the limit of what's left. And what's left is a 1 on top and a k plus 1 on the bottom. That limit is 0, which says that the left-hand side of this expression is always less than 1 no matter what x is. This is an example where any x in the world makes the original series converge. The whole number line. The interval converges over the entire number line. Okay, so I said a power series can converge on an interval, can converge over the whole number line, and it can converge at a single point. So down the way here we'll probably have one of those where it converges at a single point. Oh, I bet this is the one that it converges at a single point, because look at the expression. I've got a k factorial on top and nothing on the bottom. So here we go. Here's our example where it's going to converge for a single point. We set up our ratio test. So in this example, the ak plus first term looks like k plus 1 factorial, x to the k plus 1. Then the ak term just looks like k factorial times x to the k. I'll go ahead and put that step in there where I write the k plus 1 factorial as k plus 1 times k factorial. I'll write x to the k plus 1 as x to the k times x to the 1. Whip out the red pen and cancel where I can, the k factorials and the x to the k. Again, the x to the k, the x comes out front because it has nothing to do with k. In absolute value, keep the absolute values on it. Now we take the limit as k goes to infinity. All that's left is a k plus 1. But you know, as k goes to infinity, that's going to go to infinity. So the only thing that could possibly keep this limit to be smaller than 1, as if we didn't even have a power series to begin with, that term right there is 0. So that's our conclusion. It converges, only converges, can't spell converges, converge, converges, only for x is equal to 0. So that would make it the trivial power series, 0 plus 0 plus 0 plus 0. Okay, so the three cases were, if you get some sort of limit in here, then you solve for x and get an interval and check the endpoints. If your limit is 0, then it doesn't matter what x is. It's going to converge everywhere. If your limit is infinite, the only time that converges is if the term raised to the k power is 0. Now, my next example shows us that we can use the root test, the kth root test, as well as the limit, the general ratio test. The expression is the same, except for the root test, we take the kth root of just the ak term. And set it equal to L. To make it the generalized one, we take the absolute value of this expression here so that we'd get our x as an absolute value. Same three conclusions. We want L to be smaller than 1 for the series to converge. So I decided to use the root test on this one because if you had a long enough peek at it, all the terms in here are raised to the kth power. So we're going to do the generalized root test. We're going to set the limit as k goes to infinity of the kth root of the absolute value of the ak term. And we want that to be smaller than 1 for it to converge. So in this example, we will have the limit as k goes to infinity, the kth root of the absolute value of x plus 1 to the k all over 5 to the k. So we lose the k's. 5 is positive, so I don't need the absolute value bars on yet. And then let's keep the absolute value bars on the x plus 1. Right, the kth root of those takes the k's away. None of those have anything to do with k, so the limit of that is just the absolute value of x plus 1 over 5. Now let's solve this for x. Multiply both sides by 5. And that means that x plus 1 lives between negative 5 and 5. Let's get the x by itself. Subtract 1 all the way through, and I get negative 6 is less than x is less than 4. So far, that's our interval of convergence. But remember, we've got to check the endpoints to see if this thing possibly converges at either of the two endpoints. So we go back to the original series, and I'm going to start with the left endpoint. I'm going to replace x with negative 6. So I go back in here. Instead of x plus 1 to the k, I have negative 6 plus 1 to the k divided by 5 to the k. And so that simplifies to negative 5 to the k over 5 to the k, which I can write as negative 1 to the k, take out the negative sign, and then I have 5 to the k over 5 to the k, which will cancel. From k is 1 to infinity, negative 1 to the k is going to look like negative 1, positive 1, then add a negative 1, then add a positive 1. So this thing is going to diverge because its limit doesn't go to 0. Right? Negative 1 plus 1 plus negative 1 plus 1 plus negative 1 plus 1. So that endpoint is going to be open. Okay. Now let's let x equal 4. So I'm going to go back here and put 4 in for x. And you can kind of see before I even get it in there that that's going to diverge. So I get 5 to the k over 5 to the k. That cancels again. It just gives me a bunch of 1s added together. So that diverges because the limit doesn't go to 0. So our interval is going to be open. So our interval of convergence is the open interval from negative 6 to 4. That means if you use any x within this interval, then you'll get a power series, you'll get a series that is a convergent, an absolutely convergent series. So it's absolutely convergent when x is 0. It's absolutely convergent when x is 1. For any of those x's in there, if you kind of go back and look at the original series, we'll get a geometric series where the ratio r will be smaller than 1. Right? If this number plus 1 to the k, where x is on the other side of negative 6 and to the left of 4, will always give you a number smaller than 5. So we'll have a convergent geometric series. That's what we're looking for here, the interval of convergence. I believe I've got one more here. Got a little bit more stuff to it. So I left you a whole page here. Let's see if we can get this bad boy to fit here. Okay, so this one's going to be an alternating series, but we're using the generalized ratio test. The absolute value is going to take care of that -1 term. Oops, there should be a k. K goes to infinity. Let's get that erased. Okay, we want the ak plus 1 over the ak to be smaller than 1. So for our example, it's the limit as k goes to infinity, absolute value. You'll have a -1 to the k plus 1. Change that k into a k plus 1. Change this k to a k plus 1. And then we'll have 4 to the k plus 1. Then you're going to divide by the series as you see it. So let's flip it over. We're going to put a -1 to the k here. K, x minus 3 to the k. And up here I'm going to have a 4 to the k. And we want to know where that's smaller than 1. All right, so let's see what we've got here. I'm going to put that one step in there where I can show you what's going to cancel. You can kind of do that in your head if you want. We'll have x minus 3 to the k, then x minus 3 to the 1. We got this 4 to the k over here. A real long line here. 4 to the k, 4 to the 1. -1 to the k, k, x minus 3 to the k. Okay, so the -1 to the k is gone. And the absolute value of -1 is 1, so I don't need this term. Let's see, I've got x minus 3 to the k. This x minus 3 is going to come outside with the absolute value bars. Then we've got the 4 to the k. So all that's going to be left inside, let's see, so I'm going to put the x minus 3 out here. Everything that deals with k stays in here. So I've got a k plus 1 on top and a 4 times k on the bottom. Can you see that that limit as k plus 1 over 4k is going to just be 1/4 because of the tower of power? So we're going to get x minus 3 in absolute value times 1/4 is smaller than 1. Let's multiply both sides by 4. So that says x minus 3 in absolute value is smaller than 4, which says that x minus 3 is between 4 and -4. Get the x by itself by adding 3. And that so far is our interval of convergence. Now we're ready to check the endpoints. So let's let x equal -1 back in the original series. And our series is going to look like the sum from k is equal to 1 to infinity, -1 to the k, k, x now is -1, like that. So that's -1 to the k, k, -4 to the k, and 4 to the k. So I can put these two terms here together and share the power, -1 times -4, all to the k. So that would just give us 4 to the k. So they'll cancel. And all we're left with is this series, excuse me, which is going to diverge because the limit goes to infinity. So that endpoint is open. Now let's let x equal the other endpoint, 7. Go back up here and put 7 in for x. So you have -1 to the k, 4 to the k, divided by 4 to the k. Those guys cancel. We have an alternating series, -1 to the k times k, which is also going to diverge. In the alternating series tests, one of the things you need is the limit of the non-alternating part to go to 0, so that endpoint is open. And our conclusion is that our interval of convergence is the open interval from -1 to 7. This power series will converge when x is replaced by any number between -1 and 7. It will diverge if you use -1 or smaller. It'll diverge if you use 7 or larger. Now, one of the things that we're going to use power series for is we're going to generate functions. There will be functions that are maybe non-algebraic, transcendental functions, exponentials, logarithms, things like that, that over its interval of convergence, we'll be able to find a polynomial that fits that function for every single point. And the nice thing about finding a polynomial is polynomials are easy to do things with. For instance, you can differentiate a polynomial term by term. You can integrate a polynomial term by term. That's true for power series. On their interval of convergence, a power series can be differentiated term by term. On its interval of convergence, a power series can be integrated term by term. So you differentiate the way you think you would. You integrate the way you think you would. Differentiate, bring the power down, raise it to 1 power less. Notice that I changed the counter from k is 0 to k is 1 because the derivative of the first term is going to, the first term is a constant, and so your first term is going to be the coefficient of x to the first. So if you put in k is 1 here, you will get a1 and not a0, because the a0 will vanish. Same thing when you integrate. Here's the big deal in calculus, is that if you integrate a function, this says you can integrate the power series, swap the summation with the integral sign. That's a really big deal for you math majors. You're gonna be asked about that when you're in your advanced calculus class. And then you just integrate term by term. Add 1 to the power, divide by the new power. And you got a power series with the coefficients in front of that. And don't forget the plus c. It's a indefinite integral. So here's an example. We found the interval of convergence for this particular power series in our earlier example, x to the k over k factorial. Let me take you back there. I think that was our second example maybe. X to the k over k factorial. It converged for the entire number line. We're going to show in this example that it converges to the function f of x is e to the x. So we've shown that the interval of convergence is the whole number line. Now we're going to take the derivative of this. F of x, let me write it out, which is the sum from k is 0 to infinity, So 0 factorial, x to the 0 over 0 factorial is our first term. X to the 0 is 1, 0 factorial is 1. If k is equal to 1, I have x to the first over 1 factorial. And then I have x squared over 2 factorial. And then we'll have x cubed over 3 factorial. X to the fourth over 4 factorial, and on and on and on. Now let's take the derivative term by term. We'll take the derivative first in the summation notation. We'll bring the power down, raise the function to 1 power less. This is a constant, so it stays there. But remember, we've got to change the counter to 1 now. Let's take the derivative of the expanded version. The derivative of that one is 0, but the derivative of x is 1, so I get 1 over 1 factorial, plus 2x over 2 factorial, plus 3x squared over 3 factorial, plus 4x cubed over 4 factorial, and so on. Well, notice that this says that when k is 1, I get x to the 0, and then I have 1 over 1 factorial. When k is 2, I have 2x to the 1 over 2 factorial, and so on. So the notation in summation form agrees with the expression on the right. But that expression on the right can be simplified. 2 factorial is 2 times 1. So 2 factorial is the same as 2 times 1 factorial. 1 factorial is just 1, and this is the 3 factorial is the same as 3 times 2 factorial. 4 factorial is the same as 4 times 3 factorial, and so on. And so we can cancel. We can cancel the 2's, we can cancel the 3's, and we can cancel the 4's. And so what we'd have is 1, cancel the 2, and now I just have a 1 factorial. Cancel the 3, so I just have a 2 factorial underneath the x squared. And then the canceling the 4 leaves me x cubed over 3 factorial. Here, in the summation notation, if I cancel here, k factorial is the same as k times k minus 1 factorial. So if I cancel there, I'll be left with the summation from k is equal to 1 to infinity of x to the k minus 1 over k minus 1 factorial. But notice that that gives me the exact same terms as if I have this. Change the index down by 1 by increasing the expression in front by 1. So I found a function whose derivative is itself. And we know that there's only one function whose derivative is itself, and that's e to the x. So what we found is e to the x is equal to the sum of x to the k over k factorial from k is equal to 0 to infinity. A real neat thing would be is if you had something like Maple or Mathematica, and you graphed the power series and graphed f of x is e to the x, and they fit, the two graphs fit on each other exactly. That's kind of helpful. If I wanted to integrate something like e to the x squared, I can write the power series for e to the x squared by taking this known power series, replacing each x with x squared, and then if I wanted to integrate it, I just integrate term by term. You'll use these power series in differential equations, your Math 3350 or 3354, whichever one you take. There's a chapter on finding solutions to differential equations by starting with a power series and differentiating it and substituting it in and solving for the coefficients. So we build a polynomial power series solution. So you'll see all of this stuff again. Okay, that's it. I hope I've kept this under 30 minutes. I feel like I've talked forever, but we'll do some more examples in class.